at alkyl halide reactivity, in particular towards chemistry, actual reactions and bonds changing. Okay, so there's a little bit of nomenclature review up here. The first thing we're going to do is evaluate that new bond. Okay, so what we're looking at that's different as far as anything that we've looked at so far in lab is that we have this new bond. Okay, that carbon-bromine bond or the carbon-chlorine bond. We have a halide bond. What can you tell me about that halide bond? Anything?
Polar.
We have a polar covalent bond. Is that legible up there? Yeah, I guess it is. What else can you tell me about that? What is that going to do as far as the forces?
Dipole-dipole forces.
We've got dipole-dipole forces. And if we have a stronger force, what does that mean about our melting points or boiling points, say in comparison to alkanes? We should get higher melting points and boiling points, okay? Because we have that increased polarity. That increased polarity is also going to result in increased reactivity. Okay, so what we can do is now evaluate, we'll go off the carbon chloride. What can you tell me about that carbon where the chlorine is attached? Anything? What's its charge? What's its formal charge?
Partial positive.
Okay, partial charge is really what I wanted anyway. We're looking at a partial positive charge. Why is it partially positive?
Chlorine electronegative.
The chlorine atom is more electronegative than our carbon, draws the electron density away from that carbon. What happens to the chlorine then?
Partially negative.
Chlorine has to be partially negative. Okay? That dipole is what gives us our higher melting points and boiling points. It's also going to lend credence to our reactivity. Okay? And because students clearly had missed some of this in lecture, let's go back over some of our definitions. If we have a positive atom, okay, in particular if it's a positive carbon, we can define it as a Lewis acid or an electrophile. What is the definition? Try and break that down into the simplest definition we can. Those species are
More electrons.
electron acceptors is the standard that I usually use, but wanting electrons works. Okay, and that comes from the name of it, electrophile, phile meaning loving, so it's electron loving. If it's electron loving, what happens to its charge?
Becomes negative.
If I want to react with something negative, what charge am I? I have to be positive. Okay, so we get that opposite charge attraction. Okay, so if we find a positive atom, we can go through and say it's an electron acceptor. We're looking at a Lewis acid or an electrophile. What if that atom is a hydrogen? Do we typically refer to positive hydrogens as being Lewis acids or electrophiles? What do we typically think of when we see H+?
Protons.
We're looking at protons. We're looking at Bronsted acids or Bronsted-Lowry acid bases. Okay? So what you can do is get a quick understanding of the chemical makeup or the reactivity possibilities by looking at those individual structures and trying to determine what kind of reactivity we've got. Okay? You'll notice that in the process of forming that positive carbon, we also had that negative halide. Okay? And so a negative charge is typically something that we could also push a definition on. However, the halide kind of messes with it, okay, which is why I haven't specified what those other things could be. Okay? So if you had a negative charge, what kind of a species or what definition might we put to that?
Base.
Okay, we're typically looking at Bronsted bases. What other bases? Okay, what's the definition of a Lewis base? Electron donor. If it's negatively charged, could probably donate those electrons. So we probably have a Lewis base. Okay, what else? What's the opposite of an electrophile? Close. A nucleophile. What do you know about the nucleus? It has protons or positive charge. If we're a nucleophile and we want positive charge, what charge do we need to be? negative. Okay? Why do we not typically classify our halides, particularly in this circumstance, as acting as any one of those? How many bonds can a halide have? Whoa, darn it.
One.
It can only have one bond. How many bonds are currently shown to that chlorine? One. What's the likelihood that that chlorine with its extra electrons, what's the likelihood that that chlorine with those extra electrons would be able to share them with something else? Say anything else. Not very likely at all. Why?
It's already sharing. It's one.
It's already sharing its one opportunity to form a bond. So it doesn't make sense to look at the halide in the case of your alkyl halides as acting as anything other than just taking electrons away from carbon. Okay? Does that make sense? So what we need to do is just make sure we're clear with those definitions. That's not a very likely reaction to occur. Okay? So the next big thing that we could look at as far as reactions or alkyl halide reactivity is looking at substitution reactions, okay, which in theory is what you guys have seen in lecture. So yes.
So going back a little bit, so very generally speaking, halides are going to act like acid.
What kind of acid?
Lewis acids.
Thank you. Yes.
Very generally.
Alkyl halides are primarily Lewis acids.
Okay.
Absolutely. Okay. So if we go through and take a look at the components of a substitution reaction, we can look at an overall case here, and we can try and evaluate what things changed, and we'll look closer at that what things changed towards the end of this presentation. What bonds were broken as we transferred from the left to the right of this reaction arrow?
Carbon and the leading group.
Okay, our carbon and Lg bond were broken. What else was broken? I know I didn't balance it. That's kind of bad of me.
The M or the H with the nucleophile.
That bond's broken. Have we broken any other bonds? Less than yes? What's less than yes? No. So there's no other bonds that are broken here. Okay? Do we have any bonds formed? Yeah. We've got that new carbon nucleophile bond. Okay? So what someone went through and did is evaluated all of those bonds and said, okay, which of those are important? When we're looking at the nucleophile metal or hydrogen bond, that bond ends up being incredibly weak. So weak that we tend to ignore it. So ultimately, when we look at a substitution reaction, there's only two things that have changed. We broke a carbon leaving group bond, and we made a carbon nucleophile bond. Okay? So it's those two things that we're going to have to evaluate as far as understanding how the reaction occurs. Okay? When we look at a mechanism. We can then further break it down into the individual components. You've got your substrate, which is kind of shown in blue there. Okay? That's going to contain your electrophilic carbon. Okay? You'll notice the leaving group is also a part of that structure. We want to come up with some kind of classification for our substrates. That's where you can get primary, secondary, tertiary. We'll talk about those in just a second. The next part is you got your leaving group. Okay? That's the atom that needs to take the electrons away from carbon. Okay? In the case of your experiment today, it's going to be bromine or chlorine, or bromide or chloride. Okay? What might be something that's characteristic for your leaving group? What does the leaving group need to do? Needs to take electrons. What kind of an element might take electrons? One that's very electronegative. Okay? So electronegativity contributes to the reactivity of our leaving group. Okay? It's not the be-all, end-all, but it's part of it. The next thing we got to look at is your nucleophile. Okay? That nucleophile must be able to donate electrons to the carbon substrate. Okay? I added a little key here. You'll notice when we looked at the reaction, I've got M and H. M stands for metal. So when we have a metal and a non-metal bond, what kind of bond do we have?
Ionic.
Ionic, which would mean what charge would that nucleophile be?
Positively negative. That's what I was saying.
positively negative, exactly right. Okay? Metals typically give up their electrons, so the nucleophile would be negatively charged. So if we're looking at a metal attached to our nucleophile, we're looking at an SN2 type reaction. Okay? If it's a hydrogen, we're looking at an SN1. Okay? Just so you're aware. The last thing, which we aren't going to really talk about all that much, would be the solvent effects. That's the solution that can either help your reaction along or in some cases hinder it, depending on different properties of it. Okay? Your primary properties for your solvents, polar, non-polar. We can push the polar to the extreme and make it protic, meaning it gives up a hydrogen ion. Okay? Hence the proto part of that. Okay? So we can rank things based on polar, non-polar, protic, and aprotic. Okay? If you have a protic solvent, you're looking at an SN1 type reaction. If you have an aprotic solvent, you're looking at an SN2. Okay?
So if it has more than one to give up, would it be what, like
Oops.
diprotic, biprotic?
You could look at it in that respect. We typically don't, because as far as the solvent goes, we just care that it has at least one. Okay? So with our substrates, primary, secondary, tertiary, you should have already known those. You've heard of those, yes? Okay, we'll look at those again in a second. I like to refer to the methyl. Instead of being methyl, I like to call it, my personal favorite, for zeroary. Okay, what's a nice easy way to remember your primary, secondary, tertiaries? You look where your halogen is attached. So this carbon has how many carbons attached to it? That red one. It only has one. There it's primary. If we take a look at the next case, the carbon where our halogen is attached has two, hence secondary. And we can look at tertiary. So it makes sense, instead of referring to it as methyl, we can call it zeroary. Okay? Just kind of remembering those patterns. Okay? The last thing that I want to point out with that is all of these rankings, our zeroary through tertiary, are all pretty much referring to sp3 carbons, kind of, sort of. So they're all single bonds, no double bonds attached to those individual carbons. Okay? So when you see those definitions, you're only referring to atoms that have single bonds. Okay? What happens if you have an atom that doesn't have just single bonds? So if we now look at that carbon, okay, we won't refer to that as, say, a primary carbon in this case, if this was a CH2 out here. We'll change our definition slightly, and we'll refer to it as an sp2 carbon. Okay, why would we call it sp2? Three regions. That carbon is sp2 hybridized. Okay, so we're just going to change the nomenclature a little bit just to help us kind of classify individual substrate structures, which can help us identify reactivity. Okay. The next component is looking at your nucleophiles. Okay. As far as the lab goes, we're very isolating our nucleophiles in very particular circumstances, so we aren't testing necessarily the strength of our nucleophiles. Okay. You are responsible for understanding what your nucleophiles are and which one's better or worse than another. So if you're going to have to deal with better or worse, it helps if you know some definitions on what your nucleophiles are. Okay. So we already talked about it. Our nucleophile must be an electron donor. So the very first thing it needs to have would be donatable electrons. What kind of electrons would be easily donatable? If we take a look at methane, there's valence electrons in that. So valence doesn't quite work. Single bonds, interesting theory. Let's compare methane to water. Which one's the better nucleophile? Water's the better nucleophile. It has donatable electrons. It has electrons that aren't occupied in bonds. Okay? So we're looking for relatively high energy electrons. Lone pairs work. Okay, that's the standard. And sometimes, if you're getting really nitpicky with it, you can pull into pi bonds. We will never, ever, ever touch sigma bonds. Okay, as far as looking at a nucleophile. Okay, So now that we know what our donatable electrons are, we can start to look for other red flags. Negatively charged stands out. If it's negatively charged, it has an extra pair of electrons, so there's our donatable electrons. Okay? The next thing we could look at is lower electronegativity is typically more nucleophilic. Okay, and this one seems kind of contradictory. Okay, if we have a lower electronegativity, what does that mean as far as grabbing electrons?
Not likely.
It's not likely to grab the electrons. If I'm looking at a nucleophile, what do I want it to do?
Give them up. Not likely grab them.
To donate the electrons. I don't want to hold on to them. Okay? So if I'm going to look at nucleophilicity and compare it to electronegativity, typically the lower the electronegativity, the more nucleophilic. Okay, so let's go back to methane versus water. Okay, which atom is likely our best nucleophile in either case? Atom. Looking at oxygen and in methane, best guess might be carbon. If we compare carbon to oxygen, which one has a lower electronegativity? Carbon. Which one's the better nucleophile then?
Oxygen.
But oxygen has a higher electronegativity. According to rule number 3, it says lower electronegativity.
Oxygen has a partial negative.
Getting to the right idea, these rules are not independent of each other. They're ranked.
Yeah.
Okay? When we compare electronegativity, we must ensure that every rule prior to it has already been satisfied. So when we go through and compare carbon to oxygen, we look at rule number 1, donatable electrons. Does carbon have donatable electrons? No, which means that's immediately eliminated. Oxygen's our answer. We don't move to those further rules down the line because that's just going to complicate things. Okay, so make sure you apply appropriately. Okay? There is a red box around those top 3. Primarily, did you just ask if there was one?
Why?
No, I said
Why?
I see that.
I just want to make sure. Those are going to be the primary ones you're going to deal with this semester. Okay. The next one, size effects. Okay, that's largely dependent on the solvent. So I gave you 3 options for different polarity levels of your solvent, or if you don't have a solvent. Those rules shift all over the place, so it becomes a bit tricky to nail down. And depending on who you ask, they probably don't have it memorized, and they'll have to slowly work their way through it. I'm one of those people. Okay, it just takes time to remember that rule and kind of apply it appropriately. Okay, the last thing is steric hindrance. Should have put steric hindrance as kind of a little bit more important because we'll talk about that a lot more next week. And there's one more rule that I didn't directly mention at all, actually, because I just kind of didn't have space. At least that's what I'm going to stick with, is looking at resonance. Okay, resonance does what?
Changes the shape.
Shares electrons
Never
between
really
bonds.
changes the shape. We are moving electrons. We're moving electrons. And what bonds are we changing? Double bonds, or pi bonds. So we're changing the electronic structure of our compound by moving charge through the structure. Okay? If I'm looking at a nucleophile, I need electron density. I have to have those donatable electrons. Do I want those electrons to go outside the structure or stay within the structure? They need to go outside the structure, okay, to act as a nucleophile. So if I have a compound with lots of resonance, what is that going to say about its reactivity as a nucleophile?
Not as high.
Shouldn't be as high because I'm moving that charge into the structure instead of moving it outside the structure. Okay? Move on. Leaving group ability. We'll sort of evaluate this for a couple pairs of our structures. Ultimately, it's looking at making something the weakest base, okay, which is its ability to minimize that negative charge. So a Bronsted-Lowry base is something that wants to react with H+, donate its electrons. Okay? If we're going to look at leaving group ability, we want it to take the electrons away and hold on to them. If it doesn't want to hold on to the electrons, it's just going to end up giving them right back to the carbon, and we don't have a good leaving group. Okay? So what you're looking for is ultimately something that's a weak base. Okay? So in general, we would expect something that's electron withdrawing. Higher in electronegativity usually works out because it can polarize that bond a lot more and draw the electrons away. Okay. The other thing we could look at is polarizable, okay, which is a very fancy way of just saying the atom is really big. Whatever our leaving group is big. Because the larger we can spread that charge, or the larger area over which we can spread that charge, the more stable it becomes. Okay? So if we were going to compare some leaving groups, let's compare, why not, since we got it here, water to OH minus. Which one is the better leaving group? Okay? So we're saying these have already left. They've taken electrons away from our carbon, and they're now floating around in solution. Which of these is more stable on its own? Water. Which means what or which one was the better leaving group?
Water stable.
Still water. It's the most stable one. Okay? So in this case, what we're looking at is that, yes, both those atoms withdrew electron density, but the oxygen doesn't stabilize it very well when it's not bound to something else, say like another hydrogen in the case of water. And in that case, it ends up being a very bad leaving group. So OH minus is terrible as far as a leaving group. Water is fantastic because it's super, super stable. Okay? So as far as our actual experiments go, we are doing 2 sets of experiments. So don't confuse them. The results are separate from each other. We're trying to set these conditions up and not compare between them. We're going to run one where it's under SN1 conditions, and we'll run a second set where it's under the SN2 conditions. And we're going to look at varying the substrate within each of these sets. The reagent is going to be set already, so for the SN1 reaction, you will always be adding, I think it's ethanol, not methanol, in silver nitrate to your substrate. Okay, so what we're going to end up doing is changing what these R groups are, and in some cases changing the leaving group. Okay? And what we're hoping is that we can then monitor the overall reaction and decide, did those changes help the reaction, facilitate it, or did they slow it down? Okay?
So we'll have to run it twice then to know that?
Why would you run it twice? I'm just not sure. Why are you saying twice?
To understand how it was, to understand how your changes.
So what you're ultimately saying is we need to be able to compare, and absolutely. We are running several different substrates, and we're going to compare each of those substrates. It's 5 substrates per reaction, SN1 and SN2. Okay, so you'll end up running ultimately 10 reactions. Okay, that's a lot of reactions to do with an individual day, so it makes sense to simplify them as much as possible. So these experiments go very, very, very quickly as far as you're concerned. Okay? So we need to come up with some way to decide if the reaction actually occurred. So what we're trying to do is decide how fast the reaction occurs and if it occurs. Okay? So the easiest one to answer there is if it occurs. Okay? Because we can't figure out how fast the reaction takes if we can't visualize if it occurred. So how can we tell if the reaction occurs? Typically we look for, what was that? We want to look for some physical observation. Well, this compound is colorless. Also colorless. How about our product? Also a colorless liquid. Okay, so we've got a problem here. Nothing to observe yet until we move to our last section. And I've conveniently already got it starred. What's special about silver chloride? It's a solid. Okay, it is insoluble in water or in methanol, and we end up seeing a precipitate form. So if chloride left from the initial substrate, okay, being one of the steps of our reaction, okay, we would expect to see that chloride react fairly quickly with silver nitrate. Okay, so we add the silver nitrate to help us observe our reaction. Okay, and we would see that silver chloride precipitate. Okay, makes sense? What if the reaction takes a long time before you see that precipitate? What does that mean about the reactivity of your substrate? It's not very reactive. Okay, so what you'll do is compare those, set it all up, analyze your results. You can then go through and test it with the SN2 reaction. You'll notice in the SN2 we change the substrate. You should be able to go back, or will eventually be able to go back and compare your definitions to try and figure that out on why we switched those. We get a similar issue here. All of these things are colorless. And I'll just say that says colorless, and we'll say that says colorless too. Okay? So we can go back to our observable, and our observable in this case is sodium chloride or salt. What can you tell me about sodium chloride? Soluble in water. So can you see salt in a water solution? No. So how is that a physical observable?
You'd evaporate the water, boil the water away.
Not a bad idea, but that takes a lot of work.
What is it? You get like if something. Never mind.
It's not soluble in acetone.
We're not in water. We're in acetone. Okay. Sodium chloride is insoluble in acetone. Okay. So if there's water present, yes, it would dissolve and we wouldn't see anything. Okay. Which is why we run the reaction in acetone and we do see a precipitate form. Okay. Which brings us to our next big issue as far as these goes. Okay. In the SN1 reaction, we are monitoring the precipitate of silver chloride. Okay. Where did the chloride come from? Our substrate. Is chloride a fairly common ion?
Yep.
It's found pretty much everywhere. Say maybe even in the tap water or even in your test tubes. So what happens, let's go to the extreme. Let's say, you know what, you decide not to test an alkyl compound, so no carbons. Let's just test sodium chloride solution. What happens when I add sodium chloride to my reagents? Would I expect to see a precipitate? The silver reacts with what? Chloride. Doesn't care where the chloride came from as long as it's present. So if I add sodium chloride to my solution, I see a precipitate. Does that mean an alkyl halide reaction occurred? No, that just means there was chloride present in my solution. Okay? So one of the big issues with the SN1 reaction is we can sometimes pick up false positives. Okay? We aren't testing for the alkyl halide substitution, we're testing for the presence of chloride, or if we test it, bromide. Okay? So one of the things we have to be careful of is that the glassware is clean, that we do not have outside contaminants, say such as chloride or bromide present. Okay? Because that will give us false positives. When we move to the SN2 reaction, we already talked about this one. What we were observing was sodium chloride. And what was the problem with sodium chloride? It's water soluble. So let's say you run the SN1 reaction first. Being the good student you are, you clean out all your reaction vials to make sure that you don't get any contamination. You use your soap and water, you rinse it out, and you start your SN2 reaction. You got a little bit of water in each of your test tubes. Now when you go through to test everything, you don't see a single reaction occur. And that's because that small amount of water that you introduced to your reaction through the test tube was enough to dissolve that salt. Okay? So you end up getting a lot of false negatives in the SN2 reaction. Okay, so how can we avoid this issue?
Use new stuff.
Okay, we could always go through and use new stuff, but that gets expensive fast. How else could we do it?
Make sure everything's completely dry.
Okay, so we could spend a lot of time cleaning things. What happens when you're stuck in lab? Anything goes wrong in the experiment, what do you do?
Ask questions.
Who do you ask questions of? Your TA's busy. I'm not there. Who do you ask?
Other classmates.
You ask your classmates. You're going to do the same thing here. What we're going to do is average your results. You're going to average your results with the rest of the class. So your TA will write up on the board a chart that has all of the reactions in it, and you're going to put your information up on the board, and everybody else is going to put their information up. Once everybody's finished with the experiment, he'll go through and discuss with you those results and give you kind of an average result from that. Okay? That will allow you to draw the proper conclusions from your data. And if for some reason everything just goes haywire and something wasn't prepped right, then we know what the answers are supposed to be, and he'll also give you that information. Okay? So, We already went through and kind of addressed the bonds that needed to be broken and formed. I'm going to do this kind of fast. So we had to break our leaving group bond, and we needed to form our nucleophile bond. Okay, and I alluded to the possibility of figuring this out. So if we're going to look at a mechanism, what we want to evaluate is how did those things occur. Okay, so here's an option. We could form the nucleophile bond first and then break our leaving group. Perfectly valid way to combine those possible changes. How else could we do it? Let's break the leaving group and then form our nucleophile bond. How else could we do it? We can do it all at the same time. So someone went through and just said, these are all the possible combinations. Let's go through and evaluate each of these possible combinations. Okay? How many types of SN reactions are there? 2. We just came up with 3 possibilities. What does that mean?
One of those isn't likely.
One of those isn't likely. Which one's not likely? Nope. 3 doesn't make sense. If I form that nucleophile bond first, how many bonds does that carbon have? Remember, there was an implied hydrogen to begin with. How many bonds are there? 5. That is physically impossible, which means rule 3 can't occur. We end up with 2 types. The next part of this is trying to put together mechanisms. I'm going to draw out these mechanisms really, really fast, kind of discuss them as we go through it very briefly. If we start with, since I've already got it kind of prompted there, what we can go through and do is we'll break our bond first. When we break it, what happens to our structure? Iodide did what? Broke off how? What did it do? Took electrons. Started neutral, took electrons. What charge is it? What happened to the carbon?
Positive.
It lost electrons. It must be positive. We now have floating around in solution iodide, and we have, in this case, chloride. That positive carbon is not particularly happy. We want to stabilize it somehow. How do we stabilize a positive atom? We need to give it some electrons. Which electrons do we give it? Why do we give it the chloride? Because we already got rid of the iodine, okay? Which is ultimately all we really need in this case. And we end up with our substitution product. Okay, so 2 steps to do this reaction, yet we call it SN1. What does that 1 stand for? Refers to this first step. That's a big hint. Okay, we've got 2 possible steps here. Step 1 and step 2. Which of those do you think is the slowest step? Why is step 1 slower? I can kind of see that. What's this right here? Positive charge. Is charge good? No. Charge is actually fairly unstable. So in that very first reaction, I'm starting with something neutral and I'm going to something charged. Okay? Not a particularly nice thing to do. We're probably going up in energy. Not an easy first step. So that first step is my rate determining step. How many species are involved in my rate determining step? So we're only concerned about the reactants. How many reactants are there? There's only 1 reactant. Why is it unimolecular? 1 reactant in my rate determining step. Okay? So if I'm going to predict anything about the reactivity, how fast this reaction can go, it has to do only with that first step. The second step is pretty irrelevant. So there's a couple things we could evaluate. We could look at the leaving group ability, and we can also look at the stability of that carbocation. The more stable the carbocation, What would we expect for the reactivity? Okay. Our reactivity is based on making our final product. Okay. If I don't make the cation, can I make my final product? No. So what's going to make this reaction go faster? A stable cation or an unstable one? I know, it's kind of odd. A stable one. I must form the cation first. Okay? So what's going to determine the reactivity in the SN1 reaction is that stable carbocation. Okay? When we move to the SN2 reaction, everything happens at the same time. So let's kind of real quickly look at that. You've got the chloride coming in and attacking as the iodide leaves. What charge is that chloride coming in as? Negative. What happens when that chloride encounters more electrons? Yeah, if that chloride sees electrons, what's it going to do? It's going to repel, go the other direction. You'll notice, how did I draw that chloride attacking? From the same side or the opposite side of the iodide? Why the opposite side? Because the iodide has electrons. Okay, so the chloride needs to come in such a way that it avoids the iodide electrons. Okay, are there still electrons on the other side of that iodide? Where are those electrons found? Oops. What does this line represent? Or this line? Electrons. What does this represent? That little dot? A carbon with and more electrons around those hydrogens. So what does that say about the reactivity of the chloride? If I can put a bunch of junk in behind the backside of that iodide bond, I can limit the reactivity. Okay? Because electrons just get in the way and prevent that attack. Okay?